Our next speaker is Natalie Stewart.
Hello. Yeah, I'm one of the designated Americans, so I'm very tired. If I talk either too slow or too fast, blame American Airlines. Okay, so let me start with the photo. So I want to start this talk by telling you about a problem that got me to working on the thing I want to talk about. So in equivariant homotopy theory, or maybe equivariant K theory, there's this thing called real algebraic K theory. Where you're supposed to chuck in a ring with anti-involution, or some version of it, and you get out some C2 spectrum that's supposed to glue together algebraic K theory of the underlying and L theory. And as homotopy theorists, or as a homotopy theorist, when I see an algebraic K theory, the first thing I'm thinking is, I don't know how to do that. There are trace methods, usually. And indeed, Emanuele Dado defines something called real topological Hochschild homology. It takes in an E sigma algebra, which is, well, Mike defined it, but it's also, you can view it as a genuine equivariant version of a ring with anti-involution. And it spits out a C2 spectrum. And indeed, Emanuele figured out a real Dennis trace map, which is a hopefully pretty good approximation of real K theory from PHR. And this kind of gives you an impetus to study THR, because it might tell you something about L theory. And so in particular, it raises in me a question: how do you get structure? How do you get multiplicative structure on THR? If I throw in something highly structured into it, particular K theory can also accept E sigma algebras, and it also ends up relatively multiplicative. If I throw in something highly structured into THR, what do I get out of it? I mean, what do I get out of it? So, you know, as an equivariant homotopy theorist, I'm lazy, and the first thing I think is, how do I copy the answer from something non-equivariant and add C2s everywhere? Let's talk about it non-equivariantly. So the parallel question is, how do you get structure on THH? I throw in something highly structured, I have some functor called THH, how do I get something highly structured out? Well, you're supposed to construct a symmetric monodal structure on the THH functor, and then automatically you get a lift, right? From THH as a functor from E1 algebras to objects, you get a lift to O algebras and E1 algebras to O algebras and objects. And you're supposed to recognize, well, O algebras and E1 algebras is sort of intuitively viewed as pairs of interchanging O algebra and E1 algebra structures on the same object. So it's co-represented by a particular operad called the Boardman-Fock tensor product. So really understanding how to get highly structured multiplications on THH comes down to understanding how to compute this tensor product operad O tensor E1, right? And so you kind of wonder, in this problem of interchange, what is that? The classical theorem, proved first non-homotopically by Dunn, and then made homotopical in the operad, i.e. model independent in the operad by Leary, is, well, if I stuck in En minus 1 there for O, I get out En at the end here. So in particular, the best multiplicative structure you could reasonably ask for THH to give you, at least from this kind of symmetric monoidality argument, is that you take in an En algebra and you get out an En minus 1 algebra. And this is a general pattern. If you take some symmetric monoidal or lax symmetric monoidal invariant of E1 algebras that gives you objects, you stick in an En algebra, you get an En minus 1 algebra because of Dunn-Lurie additivity. So it's time to add C2s everywhere and profit. In the real situation, well, I claimed THR, whatever it is, it's an if you like THH as a sort of thing where you take some sort of integration over the space of configurations of finitely many points in a circle with labels in the thing, using the multiplicative structure to glue them together. THR is the same thing, but you do it in the circle with a C2 action by a flip. You consider it as the 1-point compactification of the sign representation. And an E sigma structure allows you to glue them together. And I claim that falls into this general pattern of factorization homology. And you can always give that thing a G-symmetric monoidal structure. In particular, you get a lift like this. I could throw in any G operad here, suitably interpreted. And I get a lifting from O algebras and E sigma algebras to O algebras, if you define this correctly. The sort of like pointwise tensor product of E sigma algebras. And I also claim, and I'll talk about this, that there's a co-representing object for these interchanging O algebras and E sigma algebra structures on the same objects called the Boardman-Fogg tensor product. Creative, I know. And so the question becomes, how do I take Boardman-Fogg tensor products of operads, of G operads? Or in particular, how do I tensor something with E sigma? This is exactly the question of how I construct O algebra structures on PHR. And the sort of obvious conjecture by my framing is, well, we have these little V-disks operads. These are almost the only G operads that we have. So the obvious conjecture is, well, hopefully they're additive. This is a conjecture of, no one, I couldn't find anyone conjecturing this, but it's an obvious thought. You tensor them together, you get another little disk operad, and in particular, it kind of is forced on you that it has to be the direct sum, like it has to correspond with little V direct sum W. And indeed, that's what I want to talk about today. The theorem is for an appropriate infinity categorical interpretation of all the terms involved. Well, that's true. And in particular, you get this additivity of algebras. So, and in fact, you can replace G spectra with anything you want that can accept algebras from a G operad. So in particular, you can stick in a G operad or in particular a G symmetric monoidal category there. So hopefully, if you want to prove something about G operad algebras in every G symmetric monoidal category at the same time, and you want to prove it about EV algebras, this is supposed to tell you you're going to be able to reduce it to the case of E of an irreducible representation. And of course, the corollary I've been setting up is, okay, if you take THR, you plug in an EV direct sum sigma ring, you get an EV ring, or an EV ring spectrum. That's what I want to talk about today. So having said the motivation, having said what we're going to talk about, I think good talks usually have history sections. So I want to have a history section about additivity and operads in general. And I want to engage in a little bit of historical revisionism. I claim, this is my claim, okay, the first instance of an additivity phenomenon in the category, or in the theory of operads, I think, is May's recognition principle. So May's recognition principle says, for instance, if you take algebras and pointed connected spaces over the little n disks operad, this is the same thing as n-fold loop spaces, subject to a connectivity assumption. And you can say it, like, the connectivity assumption, I probably could have said it, but it tells you that taking n-fold loops takes you from pointed n+1 connected spaces, sorry to everyone tuning in from home, equivalently onto pointed connected EM algebras, right? By taking n-fold loops and the corresponding EN algebra structure. But the corresponding structure over here, I don't need to use a laser pointer, I just want to. It's Cartesian, right? It's the same structure I started with. So in particular, since loop M is just loop n plus m, this gives you an additivity phenomenon. It tells you that these two operads have the same algebras in connected spaces. Especially if you already believe the E1 case, which I believe is due to Stashev from like about a decade earlier. So the obvious question, I say obvious a lot, the desirable thing to want to prove from this is that you can do it not just on connected spaces, but anywhere. And indeed, for the point set interpretation of everything involved, this is a theorem due to Dunn from the 80s. He proves that if you take a tensor power of the little 1 cubes operad, you get something weakly equivalent to the little n cubes operad. And there's an annoying thing about this, which is that the tensor product you put in here in the point set setting, it's not homotopical on the input. It's not really known to be homotopical on the input, even for cofibrant things. So 12 years later, Brinkmeyer proved a theorem which is quite frustratingly much stronger, which is that the corresponding thing of tensoring any little cubes with any other little cubes ends up weakly equivalent to a third little cubes and additive in the dimension. So modulo model difficulty, we had some additivity around Y2K. And then maybe 9 years later, Jacob Lurie in his collection of tomes, in DAG6 in particular, proved well for his infinity operad theory that we just heard a lot about. There's a manifestly homotopical Boardman-Fock tensor product, and this confirms that additivity phenomenon again. I'm writing En here for the infinity operad associated with the little cubes operad, and pointedly skipping equivariant things for now. But Jacob Lurie proved it's additive for the Boardman-Fock tensor products of infinity operads. And about 6 years later, Peter Ickvik and Fock proved for the original point set tensor product that we don't know that it's homotopical on cofibrant operads, I think, but for cofibrant operads, which are equivalent to En, we have the additivity theorem anyway. So if you can prove that it's left derivable, you're going to get in the point set setting a derived additivity theorem. And that's pretty much where it stands in the non-equivariant setting. We know in pretty much any model the best you can ask for. Now moving along in the equivariant setting, well, Work-Sanderson have the analog of May's theorem. You have to ask for little disks, not little cubes, because what is a cube in a representation? But they have an additivity for the little disks operators. These are exactly interpreted as in Mike's talk. And the tensor product is, if you like, the Boardman-Fock tensor product of operads with values in a symmetric monoidal category. That's what I mean here. And this suggests an additivity theorem in the point set world, which was proved last year, or at least put on the archive last year by Ben Chesney, which is equivariantly about the strength of Dunn and Brinkmeyer's proof. And the end of this history so far is that there's a draft on my website for Lurie's version. That's the history. So, because I'm obsessed with history, let's also talk about a little bit of history of geometry. I promise there's a point to this. I'm introducing mathematics while I do this. Yeah, so getting into the content a little bit. Starting from maybe around Mike's talk. Around 2016, in the wake of Mike and Mike, not to be confused with Mike and Michael. In the wake of Mike Hill and Mike Hopkins' work with Doug Ravenel on the covariant variant problem, they wrote down this beautiful paper, Mike and Mike, about G-commutative monoids and genuine equivariant algebraic structure, which cemented, at least in my mind, the notion that like there should be some G-commutative monoid theory. And a great model for it is semi-Mackey functors. So I'm gonna assume you all are very happy with. They're like Mackey functors, but you don't assume that the things are abelian groups. You assume that they're commutative monoids. And in a Lurie-esque maneuver, about 6 years later, Nardine and Shaw put out a paper called Parameterized and Equivariant Higher Algebra that very straightforwardly generalizes Lurie's model for infinity operads there. In particular, Lurie's model comes from thinking about special gamma spaces and the category gamma hop and talking about some kind of fibrations over it. They do some kind of fibrations over some kind of genuine equivariant version of gamma hop. I think that that's really hard. So I'm happy that Shaw Barkan, Runa Haugsung, and Jan Steinebrunner came later the same year proved that you can do it all over the effective Burnside category instead. And in fact, this subsumes a proof of a James Cranch's theorem that special gamma spaces are the same thing as productors or as Mackey functors for the trivial group. You can prove this on the level of the theory of operads, and adding a G is part of what that paper was doing. So that's the model that I'm gonna stick with. We can do some sort of fibrations over span finite G sets. Hopefully so that, well, the co-Cartesian fibrations end up being unstraightening of semi-Mackey functors valued in infinity categories, which are my model for G-symmetric monoidal infinity categories. Going forward a little bit, in history, there is a co-representing object for homotopy-coherent interchange, Orton-Talk tensor products. You can find it in a paper that exists, and I promise it's not really long and complicated. And in particular, there's also a monadic forgetful function, a conservative one to G-symmetric sequences, which you can find over there. I'll go over it. And a recent paper, just to give a little bit of a guide, a recent paper that I put up a couple of days ago goes over algebras in Cartesian and co-Cartesian structures, which I'm going to implicitly use a lot of results from there, but they're what you think they are. And this is kind of the history, the oral history that I'm going to use today, just in terms of the canon of infinity categorical G operads. But that's that. Let's get into a sketch of the proof. And if I had a million years to give this talk, this would be a table of contents. But this is the diagram, which shouldn't make sense then. What I want to talk about for this group is, okay, we're gonna have to define some kind of lax version of G operads that allow us to do some sort of model-y stuff. And we're gonna call these G pre-operads. If you like higher algebra, kind of like pre-operads. So that all the things in the middle of this diagram are just pre-operads, not operads. And it's gonna be a localizing subcategory. And we're gonna define some models, some convenient models. Products, Reith products. If you're familiar with the May-Thomason theory and the Boardman-Fogg tensor product there, which co-represents pairings, that's what's going on here. And we reduce once we know that these are models for that to showing that this is a local equivalence, i.e. it becomes an equivalence after you localize down to G. And the main content of this strategy, once we reduce to showing that this is a local equivalence, will be to talk about a well-controlled theory of approximation that allows us to pull this back to some more convenient situation. These PV operads, which if you like factorization homology, are supposed to be operads for equivariant prefactorization algebras, and you argue there. In particular, we're going to do there's an image factorization that shows up in this proof. You have to recognize that on the prefactorization level, where everything's topological, you're going to have to realize some version of Dunn's argument that the tensor product is an equivalence onto its essential image, i.e. we verify that this is a local equivalence. And we have to verify that its image is equivalent essentially to the entire operand in the codomain, which in this case recognizes that not just the approximation we start with, but when we take its sort of image, it remains an approximation. Which comes down to checking that little direct embeddings are decomposable in this sense. Right, that's how this works. I want to go through a little bit more carefully. I'm not gonna have time to, but we'll go through a little bit more carefully this strategy, but this is how you prove it essentially. So to make this make a little bit more sense, I want to talk a little bit about what pre-operads are and then probably end. But to do so, I should talk a little bit about what happens when you believe Elmendorf's theorem really hard. So I might define G operads, for instance, as operads which are enriched in a Poinsett way in topological G spaces. And we have Elmendorf's theorem, which tells us that those things are the same thing as presheaps on the orbit category. I.e. they're the information of the genuine fixed points for every subgroup connected by restrictions. But there's a little bit of trickery happening. which is that when you talk about operads, they're Borel equivariant in the symmetric group. A symmetric sequence, a weak equivalence of symmetric sequences is something whose map on the sigma n set of n-area operations is an equivalence on underlying. So we can't just say genuine G times sigma n equivariant on the nth level to describe that homotopy theory. We have to describe things which are Borel in this variable and genuine in this variable. This is why these graph subgroups show up. And just to stop mincing words, you can define a weak equivalence between these to be something which is, well, it's a map between G operads which induces equivalences on the genuine fixed points for all of these graph subgroups. So we're only seeing the things, essentially only seeing the transitive G times sigma n sets whose underlying sigma n sets are free. So it's a Borel in the sigma n variable. And this is the homotopy theory that we're going to do for G operad, generally. And when you take this perspective like really, really seriously, you find some definitions that show up in the work of, for instance, Peter von Bencher. When you look at the operatic composition map and you take genuine fixed points everywhere and unwind what it's saying, you get some expression where you compose, you know, these equivariant areas. You end up with an index coproduct over here. And you get a restriction action, and you get actions not of sigma n on these like graph fixed point subgroups, but of the equivariant automorphism groups of each of the sets defining them. And you can in fact get an equivalence between a model structure on Mike's definition and a definition built on this. This is in the paper Genuine Equivariant Operads by von Bencher that I have. And this is kind of where I wanna go from this. See, in the infinity operad type model, we're really thinking about that. See, you're supposed to recognize, or one thing you might recognize is that like, this is secretly telling you, I have this set mapping down to S, and the map down to S gives me this decomposition of this. I map H sets from this to S. When I look at a map down to S, it expresses the domain of the thing as an S indexed coproduct of all of its fibers. And so why not define this as something fibered essentially over maps of finite G sets with some sort of inert information that implements restrictions and whatnot. This is the idea behind the things. So a G pre-operad ends up being defined as a map to the effective Burnside category with co-Cartesian lifts over backwards maps. Meaning there's some sort of like contravariant functoriality along the backwards maps, or covariant along backwards maps that implements restrictions and whatnot. And we ask for it to be a G operad that there's some sort of Siegel conditions. And algebras in this setting are just maps that preserve the co-Cartesian lifts for backwards maps. Now these Siegel conditions are telling you that when you have a map, are essentially telling you that the relevant structure spaces are these products. Yeah, they tell you essentially what you need to know that this structure map is just composition of AeroCAD, or composition when you like unwind what these structure spaces must have been in that like sort of genuine operatic thing. Just for a little bit of notation, it ends up being a localizing subcategory. These Siegel conditions are stable under limits, so it ends up being a localizing subcategory in the sense of infinity categories. And I tend to use L of G for the localization. Oh wow, okay. Okay, there's an underlying G symmetric sequence, it's conservative. There's EB operads, they work the way that you think they do. Algebras look like actions of the structure spaces on these like equivariant mapping spaces. Examples are loop spaces, G spectra. And the thing I really want to get at is probably this definition. The point I'm trying to get at essentially is that like after saying everything, you do a lot of topology that really looks like a non-equivariant setting, and you really have to like bite down on the idea that we have a pre-operatic model for the Borden-Fock tensor product. We have something that co-represents interchanging algebras, which is, well, if interchanging algebras are these kinds of pairings in the sense of may, well, this push forward over here is something that co-represents it. But it doesn't satisfy the Siegel conditions that we wanted. But we have some formal way of doing that called L-op-G localization. And you just have to develop some category theoretic tools called approximations, whose definitions are here to do that. And you do it. I guess that's all I have time for. But, yeah.
Can we see the factorization homology slide that you quickly?
Which one is the factor? Are you looking for the done map slide, the one with the
I don't know.
biology textbook looking thing? Yeah, this is the done map. Like the idea here is you need some map from some model for EV tensor EW to EV direct sum W, and it works like the non-equivariant thing. Once you model it as some sort of Reed product, which is generated by these formal compositions where you have some element you might want to compose from EV, and then over that, some elements you might want to compose into it from EW. You need an element of EV direct sum W. You recognize that disk in V times disk in W is diffeomorphic to disk in V direct sum W, and you use that to sort of represent those elements of the Reed product as just living in V direct sum W, and forget how you got there. And that's the map going like that. And the topology of this argument is recognizing that these decompositions are unique. And if you shrink little V direct sum W disk like embeddings in a very nice way, you can deformation retract the space of all of them onto ones that came from this procedure. That's what this, surely that's what this slide is communicating. Are there any other questions? Yeah.
So do you somehow learn from the Reed product operation, whatever it is somehow symmetric, even though it's not supposed to be?
Yes, it's sort of, I would be surprised if it was symmetric on the level of pre-operads, but it becomes symmetric after you localize the G-operads. I mean, it's in the same way that it's kind of surprising. I put down my clicker. It's kind of surprising that when you take this thing itself, it's kind of surprising that it's symmetric, right? But it's just everything eventually comes down to there's some symmetric monoidal structure, and everything is coming from it. Other, yeah.
What about backward maps?
Sorry, again?
What about backward maps you have mentioned?
Thank you for that question. The observation, or maybe not observation, the definition that I'm implicitly using, I was hoping that someone would define a Mackey function for me in this conference. This all is fibered over the category I called span finite G sets, which some people who are more algebraic geometry coded might prefer as a category of correspondences in finite G sets. It has objects, finite G sets, morphisms. Ignore that little one, is spans. Say morphisms from X to Y will be a span going like this. So you pick an object R and you pick a backwards map and a forwards map. And there's two cells and no higher, which correspond with isomorphisms of spans. When I say backwards map, I mean map whose forward map is just an isomorphism. And when I say forwards map, I mean map whose backwards part is an isomorphism. So up to relabeling things, it comes down to like only telling you the forwards information for forward, only telling you the backwards for backwards. There's a whole factorization system between those two things. And yeah.
Treat it's like we are more than
Sorry, say it again?
we are more than one, something like that.
Yeah, it's a quirky way, I think essentially due to Lindner of finding a way to make category theory handle the double coset formula, essentially. That's like the whole point of it. It's weird. Are there additional questions?
If not, then we now have another coffee break. The next topic starts at